All set? Okay. Thank you very much to Lucas and Natalie for the invitation, and to everybody for coming. So my talk will be about quantum character varieties. And topological field theories. So of course it's supposed to be a lecture, and I have some time, so I will try to be I should say here. I try to be as self-contained as possible, but of course don't hesitate to interrupt with questions. I've prepared the first few lectures, but how fast we are going and what we are going to do next is entirely up to you. So don't hesitate to suggest a few things. And I should say that I've put some sort of web page on my website with some maybe useful information, so you can check this out. In particular, I've put here a tentative plan, and I also have put a list of reference with actual links to the article. So I will sort of freely use this reference list during the talk, basically. So let me start with a brief outline of what I'm planning to do. So can you see if I'm writing here actually, or is screen? Yeah, okay. So the central object I will be talking about is something called the character variety. So let me fix V be a n-dimensional vector space over C. And for pretty much all this talk, I will fix G to be GL of V. Sometimes I will actually switch to SL of V. They are both convenient for different reasons, depending on what I'm talking about. So everything I'm going to talk about also works for more general, say, reductive affine algebraic group, but for sake of concreteness, I want to work with GLV. And so if S is a topological surface, I guess I want it to be compact. That might not be necessary. I definitely want it to be oriented, and it may have boundaries. It may have a boundary. Okay. And now to this data, attach this thing called the character variety, or I should say the G character variety, but I won't do that, of S, which basically, let me put codes for no, because I will be more precise later, but it's basically the space of n-dimensional linear representations of the fundamental group of S up to equivalence of representation. So that's the same thing as just group morphism from pi1 of S to G. And remember here, G is always GL of V modulo the action of G by simultaneous conjugation. And I put quote here because I have to be precise about what I mean by these quotients. And actually there will be some sort of subtle point about it, which is kind of the central idea of this lecture, but I'll come back to that later. Anyway. So one of the main features of this character varieties of surfaces, so they are, of course, they are very interesting objects. And pretty much by definition, they are the crossroad of topology and algebra, because we're studying representation. And the thing that this character variety, as the name suggests, is not just a set, but it's actually a geometric object. So there is some geometry involved as well. And so somehow one of the original motivation, if you replace one of S by any discrete group, is somehow to have like some geometric ways of studying representation theory of infinite discrete group. So if you're working with a finite group, you just have to study the set of characters, but for an infinite group, this is a variety of characters, basically. And one of the main features in the particular case where this group is actually the fundamental group of some surface is that this has a Poisson structure. So it's been discovered by Attia, Bott, and Goldman. So again, the links to the actual paper are on this webpage I was mentioning before. So it says there is a Poisson structure on this. And it turns out that this Poisson structure, as one should expect, is related to some like physical theory, and in particular the like two-dimensional Yang-Mills theory or three-dimensional Chern-Simon theory. So it definitely like shows up naturally in the theory, and somehow that explains why it has anything to do with knot theory and topology and whatever. Anyway, so it turns out that these varieties can be described in at least two different ways. So if I want to somehow compute these character varieties and understand them, there are actually at least two different ways to do that, which are pretty different. And each of them are like some good points or some drawbacks, basically. So one of them is combinatorial. And what I mean by that is more or less that I need to choose generators for by one of so that's not entirely correct. That's enough to describe the character variety, but not the Poisson structure. So really what I mean is some sort of like combinatorial representation of my surface. Okay. And then the other description is topological. And it basically involves like loops, or I should say free loops. So loops without the base point on X. And in both cases, you get some description of the character variety itself and of the Poisson structure I was mentioning before. And accordingly, there are like two sort of independent construction of a quantization of this Poisson structure. And so they were developed more or less at the same time, but by sort of different people. So on the combinatorial side, so there is a combinatorial quantization using quantum algebra on quantum groups. So I will, of course, come back to that later. And on the topological side, basically, the idea is that you need to replace loops on the surface by knots in your secant surface. So that's something that people call skein theory. Okay. And basically, what I'm going to do in the first half of the lecture is basically try to explain all of that. I don't know if that's the best idea, but I will try to sort of switch between those two points of view, like work of both of them in parallel, basically. And then basically, so it's kind of clear that these two approaches of quantization of this Poisson structure should give the same results, but actually it wasn't really like proved in the literature except maybe for SL2, and also it's some of like I don't know, even if you manage to prove that, somehow you have to prove it by hand. It might not be very satisfactory. So somehow the main goal of the lecture will be to reformulate and generalize I should say this is the goal. All of that in the language of topological field theories. So basically what I'm saying is that I want the best of both worlds somehow. So I want basically what I want is that I want a canonical, purely topological construction. So I want something, I want a definition which doesn't involve any choice, which is compatible with gluing of surfaces along boundary. So that's basically what it means to be a topological field theory. But I also want it to be easy to compute. And of course, I will explain this in more details later, but somehow the key point, as I was mentioning before, is that Bose's construction gives you a description of the algebra of neural functions on the character variety. And the sort of main idea behind what I'm going to talk about is that I want to replace this by the category of sheaves on the character variety. So really what I'm doing is that I'm looking at the character stack, but I don't know what the stack is. You don't need to know what the stack is either. So I will explain that, but basically the main idea is to work with the category of sheaves on this character variety. And so I know most of you probably have a more topological background, so let me give you an analogy with something you might be familiar with, and if you're not, just forget about it. And this is actually much more than an analogy, but again, I will go back to that later. Oh, sorry, I should
switch cameras.
Yeah, done. Thanks, whoever that was. So an analogy to be more precise so if you're a topologist, maybe you care about the space of nodes or links. Say in R3. So even if you're really only interested in like links in R3, it's actually a good idea to look at something that seems more complicated, but is actually simpler. So the main problem is that somehow this space doesn't have nice algebraic structure. So you can't like, it's hard to do computation with that. So it's actually better to replace it with something called a category of tangle. Tangle. So this category has objects, finite sequences of symbol plus and minus, and the morphisms are, and I should say framed, whatever that means, don't worry about it, oriented tangles. And basically a tangle is just like a piece of a knot. So something like that, I don't know. This is an example of a tangle. Let's say. So this is a tangle. So this is a morphism from plus, plus, minus to plus. And the sort of very basic idea is that this category seems to be more complicated. So it's a category, first of all. And those things are like, seems more complicated than not, but actually they are simpler. Because when you're working with that category, you can take a links or not and chop it into elementary pieces. And it turns out that this category has a very nice algebraic structure. So it has like some sort of generators on relation presentation. So it has a very small number of generators, and it has many relations. But it turns out that many of these relations just sort of formally follows from the fact that it's a certain type of category. So in fact, many of these relations are kind of automatic. And so you have a very few number of relations to check. So if you want to define a link invariant, in fact, you better define a functor out of this category by just specifying its value on the generator and just check the relations. So not only it's sort of easier to do, but then you get an invariant which is compatible with like cutting, links in smaller pieces. And so it's automatically compatible with a lot of structure. So somehow this is the analogy I want you to have in mind on how does it relate with what I was talking about. So as I sort of suggested what I just erased, so the space of links has very much to do with functions on the character varieties. And this category of tangles has very much to do with the category of sheaves on the character variety. I should say quasi-coherent sheaves, but whatever. So the basic idea, again, is that we are looking at something that sort of looks like more complicated, but it's actually better behaved. And at the end of the day, it's actually simpler to handle. So that's basically it. Okay. Yeah, I mean, I hope that was pretty obvious, but I should say that in particular in this category, you have the empty object, which is just the empty list. Yeah. Oh, sorry. Yeah. Sorry, I should have said something here is that in that category, the space of endomorphism of the empty sequence is precisely the space of link. Yeah. And in the same way, we'll see here that this category of sheaves has some particular distinguished object in it, and endomorphism of this object will give you back the function on the character variety. So it's contains like strictly more information than that, but it's actually better behaved. Okay. Are there any questions so far? Check I didn't forget anything. Okay, we're good. Okay, so let me start with the first part, which actually will be fairly long, I think. So maybe at least 2 lectures. We'll see. It's so about the various definition of this character varieties. So I will start by the general definition, and then I will tell you how to run this combinatorial on this topological description. Okay, so to be slightly general, let gamma be a discrete group. And I probably want it to be finitely generated. Okay. Oh, no, I still have one here, sorry. I'm not very good at handling this. Yeah. Okay. So maybe I should write definition. So the representation variety of gamma is by definition the space. And again, I should probably say the G representation variety, but for me, G is fixed. And it's just the space of group morphism from gamma to G. Okay. And so as I mentioned, it turns out that this is not just a set, but actually a variety. And the idea is that if you choose generators on relations for gamma, say x1, xk, on relation R1, L. So by which R1 is a word in the free group generated by x1, xk, which is supposed to be 1 in gamma. Yeah. Yeah, I don't think you need to. I think finally generated is enough, but it's just simpler with that. Well, this will be the case for fundamental group of surfaces anyway. So yeah, let's say finally presented. That's better. And so the basic idea is that how do I construct a representation of gamma? Then I need to choose basically a matrix for every generator, and I have to check that this matrices satisfies this relation. So it means that I can embed this representation variety into g to the power k, and I can describe it as say a set of k tuple of matrices which satisfies this relation. So I write it like this. Okay. And somehow the point which I think is fairly obvious is that this thing is like a polynomial equation. In the coefficients of the xi. So the idea is that somehow like G itself is like an algebraic variety. It's defined by some polynomial equation. You could also just like choose matrices in just the vector space of all non-necessarily invertible matrices and add as a relation that it should be invertible. But at the end of the day, the idea is that this thing is defined by a polynomial equation in some, in the vector space of n square matrices. So in particular, this gives this thing as the structure of, I don't know, let's say an affine algebraic variety. Maybe that's redundant, I don't know. Maybe it's called an algebraic set. I'm not sure. Like a set of zeros of polynomial equation in some vector space. And something that's maybe not entirely obvious is that for any two presentations of gamma, the corresponding algebraic varieties are canonically isomorphic. So it's not obvious. Like if you change the number of generators, it seems that they live in like even different space. It's maybe not too surprising they are isomorphic, but in fact they are kind of isomorphic, which is of course much stronger. So this algebraic variety structure is like completely well defined from gamma without. I mean, there are ways to define it without choosing generators and so on, but it turns out that somehow there is an abstract definition by some universal property, and then you use a particular presentation like this to show that this actually exists. Okay, so far good. Let me check my out. Oh yeah, that sure. That definitely makes sense. Okay. Okay, here we go. So in particular, well, I will come back to that later, but it makes sense to consider like the representation variety of a surface, which by definition will be, sorry. Okay. So in particular, I can choose a base point in my surface and consider the fundamental group, and then I can look at the representation variety of that. So I just wanted to mention here that it does not depend, of course, on the choice of X, but non-canonically. That's a lot of negation. The thing, of course, as you know, if you choose a different base point, then basically the two groups are conjugated, and you need to choose a path between your different base point. And there is, in general, not a unique path. So this representation variety as a set and as a variety, it kind of depends a little bit on the, I mean, it doesn't depend on the base point, but like there is no canonical isomorphism. But for the character variety, we'll see that's not the case. Okay. Now again, I think many of you are probably familiar with that, but recall that if G has again some affine algebraic variety, or maybe some affine scheme, yeah, I should say that this representation variety is actually the set of C points on some affine scheme. So there is like a more involved structure above it, but I don't want to talk about that. But in general, if you have an action of a group on some algebraic variety, then if you just take the quotient naively, the result doesn't have any like natural geometric structure. So the sort of natural thing to do is, instead of like trying to just naively take the quotient, I want to describe what the function on the quotient should be. And well, the only sort of natural thing to do is to define it that way. So the affine quotient, it's usually denoted with a double bar here, but I will probably forget to do that later, is defined by saying that so what are polynomial function on these quotients? Well, in particular, there should be polynomial function on X. And the only reasonable thing to do is to ask that the invariant part of the algebra of polynomial function on X. Okay, so the action of G on X actually gives you an action of G on this algebra. And it turns out that this is compatible with the multiplication. So the part of the claim is that the multiplication of this algebra is a map of G module. And let me say this in a more fancy way. Because I will need something like that later. So really the sort of fancy way to say that is that O of X is an algebra in the monoidal category of representation of G. If you don't know what that means, just forget about it. But basically, so the category of representation of G, and I mean algebraic or integrable representation, whatever. It's a monoidal category, which means that you can take tensor products of modules. This map is a map of module, and then you can write down associativity in terms of diagrams and whatever. So this is something called an algebra object in this category. So this is really just a fancy way of saying that, but I will need this fancy version later. But the main point is that because the multiplication is a map of G module, then taking invariant actually gives you an algebra because it's compatible with the multiplication. Okay. But the thing is that this algebra is not, and I think on that in general, just like some space of function on the sort of set theoretical quotient. And to give a sort of textbook example, if you look at the action of G on just the space of all matrices by conjugation, well, the thing that polynomial functions in particular, they are continuous. And the space of diagonalizable matrices is dense in that space. And because I want to look at polynomial functions which are invariant by conjugation, then on the space of diagonalizable matrices, they are determined by the value on actually diagonal matrices. So somehow this space of how should I say that? Yeah. So this quotient of the space of all square matrices by G. So basically, this thing is only like diagonal matrices. So somehow that's the claim. So this thing is actually the same thing as diagonal matrices up to the action of the symmetric group that just permutate the element on the diagonal. Okay. So in particular, you just see like one sort of big down subset of this space, but not all of it somehow. Okay. So basically, there are like two ways you can think of that. Either it means that you can, when you construct this quotient, you can actually restrict to diagonalizable matrices here. So you can take a subset, and on this subset, the affine quotient is just the actual quotient. Or you can like keep this whole thing, but say that there are like some non-diagonalizable matrices that are not in the orbit of diagonal matrices, but they happen to be in the closure of this orbit. And the idea is that this quotient is actually the space of closure of orbits, basically. And why this example do matter for us is that somehow there is a mild generalization of that. So in particular, pretty much the same argument tells you that if you look at the representation variety of Z, for example, sorry, the character variety, decidedly. So what is the representation of Z? I just need to choose one invertible matrices. So that's the space of invertible matrices up to conjugation. And of course, the exact same phenomena appear. So that's the same thing as invertible diagonal matrices. Modulo the action of Sn. But I want to reformulate this again, sort of maybe a little bit too fancily. But in that case, an invertible diagonal matrix is the same thing as a semi-simple representation of the modulo equivalence. So basically, you can map the generator of Z to like any matrix. But if you just happen to choose a diagonalizable one, it means that the representation is actually, you can decompose it as a direct sum of one-dimensional representation. Yes? Where? Here? Oh, here. Yeah, here I question by the action of G. Yeah, yeah. Yeah, what I denote by error of gamma is without quotient, the character varieties is a quotient. Okay, yeah. Oh, sorry, yeah, sorry, Natalie was asking if I was quotienting by G here, and the answer is yes. So the representation variety is the space of representation, and the character variety is the space of representation modulo G. So for the representation of Z, saying that you send a generator to something which is diagonalizable, just mean that the representation is semi-simple. It's a direct sum of irreducible representations. And because it is abelian, irreducible representations are just one-dimensional. And it's actually a general fact. So again, I have a link to a book on this page I was mentioning. I actually forgot their name, so I'm sorry. I think the second one is Majid with a G. Anyway, I mean, I don't claim that they proved it, just as this book explained this pretty nicely. So the idea is that for any gamma, there are bijections between so the points of the character variety of gamma, the equivalence classes of semi-simple G representations of gamma So just like in that example, actually this character varieties, this affine quotient sees only the semi-simple representations and not all of them. So the idea is pretty much the same. Like you need to look at closure of orbits, and the closure of any orbit contain a unique equivalence class of semi-simple representation. And then it's also in bijection with a set of again n-dimensional characters of gamma. So recall that if I have a representation, then the character, I don't know how to draw chi, is the map that map an element of gamma to the trace of rho of x. So those are very useful tools in representation theory. So you're probably familiar with those. The main point is that in general, how should I say that? Like characters are actually additive on extension of representation, but somehow they can't tell if that's a non-trivial extension or a direct sum. So two different representation, non-equivalent representation may have the same character, but not if they are semi-simple. So the claim is that two representation of gamma, which are semi-simple, have the same character if and only if they are equivalent. So that's how you get this bijection. And of course, that's why this is called the character variety. Okay. So let me emphasize that this statement is not true if I replace G by any other group, but we still call it the character variety. So it's still somehow that's the origin of the name. Okay, so far so good. Yeah. Yeah, that's sorry. So the question is whether it makes sense to work with the fundamental group and not choose the base point. And the answer is yes. In fact, I will explain a bit later that it's actually clever to choose like a finite set of base points, like several base points. I mean, this is a very good point. In a way, the whole point of working with category of sheaves on the character variety, I'm not sure how to make that precise, but it's a little bit like working with a fundamental groupoid, or rather with every possible fundamental groupoid for every choice of base point, of set of base point, basically. So this is, yeah. I mean, behind this, there is the sort of, there is an idea which is very common in math and maybe even more in physics, which is whenever you have to make some choice on a down one to just like average over all choices. And somehow the main construction I will present at the very end of this lecture is kind of an incarnation of this idea. Anyway, okay. Okay, so here goes a description of character varieties in general. So they are, bijection with a set of characters, but of course, if you try to define them that way, you don't see like the geometric structure. So again, the whole idea originally is that for finite groups, you just have like a set of characters and it tells you everything you need to know. But for infinite discrete group, having this geometric structure is actually important. So you don't want to define it that way. But it turns out that this gives you information about the character of this representation. So now, of course, I want to emphasize that if gamma is actually the fundamental group of S with respect to some base point, then the character variety of S, which by definition is the character variety of this group, is this time it's canonically independent of X. Of X. Because I mod out by the action by conjugation, and because two choices of the base point are conjugated, maybe in, not in a canonical way, but they are. But because I mod out by conjugation, it doesn't matter which path. Like if I choose a different base point and I choose two different paths, the representation variety can tell that, but not the character variety. So at the end of the day, I have something that do not depend on the base point anyway. No. Okay. No. And so in that particular case, there is somehow like a preferred description. So if I want to be even more specific, and let's say S is a surface of genus G with n boundary components, and I want n to be at least one. Okay. So somehow, this is something that will show up a lot during this lecture, is that the case of punctured surfaces is actually much easier. And there are several equivalent ways of saying why it's easier. One of them is that's because a fundamental group is actually free. So in that case, the fundamental group of S is just a free group of 2G plus n minus 1 generators. Again, you probably all know that, but let me recall that. So here, I have a distinguished boundary component here. And then I may have others here, maybe. And basically, for every handle like this, you have something that loop around here. And you have something that goes behind here and back, so that I don't know, I never remember the convention. Let's call it AI, and this one BI. And then you have loops around the boundary component, that I. So in particular, it means that the character variety of S is actually like you don't even need to, you don't have relations in that case. So it's really just a bunch of copies of G modulo G. And now if n is 0, then basically what you want to do, so if n is 0, suppose you don't have that, and you have only one boundary component. And if you want to close it, basically you want to say that the monodromy around this is trivial. And so what happens is that you have the same, you actually have the same generators, and you don't have that because, yeah, sorry, let me try to get this right. And the relation is at the product of, I should write it like this, I, BI, 1, where this bracket here is a group commutator. So again, basically, if you assume that you don't have, you have only one boundary component, and you try to write down a loop around this puncture, it's actually the product of the commutator of this generator. And basically, you just want this to be 1. Okay. So again, there is a sort of like fancier way to formulate that, is that if, say, S naught is, I take S and I just cut out the disk. Okay, so now this guy has one boundary component. And the claim is that the monodromy, like taking a loop around the unique, in that case, boundary component, gives you a map from the representation variety of, sorry, S naught for whatever base point I chose to the representation variety of an annulus. Let me do it that way, which is just G. Okay. Like the fundamental group of an annulus is Z, so the representation variety is G. So I get a map from this guy, which is just a bunch of copy of G, to one copy of G. On that sense, like if I have, so an element in this is just a bunch of matrices, like with no relation. And this maps this to the product of this, and again, capital letters mean matrices here. So it's a product of this commutator of matrices. Okay. And then by definition, in that case, so I want, the new relation I want to add is that this guy should be the identity matrix. So this character variety is the inverse image of the identity modeled by G. So basically, I have a description for punctured surfaces. And then if I want to sort of close the boundaries, this is how you do it, basically. So really, this is just a way of rephrasing the fact that the representation variety is defined by choosing a bunch of matrices and then asking that this relation is true. But we will see that this map has actually some nice property, and this will be useful later for the, when I want to describe the Poisson structure. So that's why I'm doing it that way. Let me maybe check the time. Oh. Let me see. No, I think it's, no, it's probably a good place to stop, I think. Okay. yeah, so thank you very much. Is there any questions at this point?
Sorry, maybe it's an artifact of the camera, but written after taking a loop around the something boundary component.
Around, I say unique in that case.
Unique. Okay, thank you.
Yeah, because I start with a closed surface and I remove a disk. So I just wanted to emphasize that I did that basically.
Okay, right.
Oh, that's what I did. Yeah. And yeah, question or maybe comment. I don't know, like if it's too elementary or too fast or whatever. Just complain, please. Okay, so. Yeah.